Thank you very much. It's a great pleasure for me to be here, and I want to thank the Center for Smart Infrastructure and Construction and for the University of Cambridge for hosting this talk. It's really nice to come back, and I think that the work that's being done by the center is extraordinary, and I'm very interested and looking forward to our meetings tomorrow when we hear about some of the exciting research which is being performed. My talk tonight is called The New Normal for Natural Disasters. And the new normal is probably a phrase that's been a bit overused at this point, but it's originally attributed to Mohammed El-Arian, who was the chief executive officer of an investment company called PIMCO. And El-Arian coined the phrase to represent the state of the world financial affairs after the 2008-2009 financial crisis. Now, I think it's quite appropriate to start on that premise because that crisis was accompanied by perhaps the largest exercise ever conducted in public risk awareness. It substantially altered our perceptions of the risks associated with investments, banking systems, and the stability of the world's largest financial institutions. 2 years later, 2011 and 2012, especially when put in light of the events of Hurricane Katrina, should also, I think, be considered a similar watershed with respect to natural disasters. And it's in this lecture that I would like to persuade you that we can and we should never return to the state of mind that preceded 2011. We have, in fact, all been normalized in a way by the years, those years and the events of those years that requires a serious re-examination of the risks related to natural hazards and the very definition and protection of our critical infrastructure. To address these issues tonight, I'm going to cover three major topics. The first topic, I'm going to talk about earthquakes. And I'll talk about the TOHOKU earthquake and tsunami, and I'll talk about the Canterbury earthquake sequence. Sorry, I'm going backwards here, hold on. I'm going then to talk about hurricanes. I'll talk about hurricanes in New Orleans and hurricanes in New York City, and then I'll say a few words about the new normal. So let's begin with the TOHOKU earthquake and the Canterbury earthquake sequence. The TOHOKU earthquake was a 9-moment magnitude earthquake. It's the 4th largest that was ever measured. It actually had an astronomical consequence. It shifted the axis of the Earth by about 25 centimeters. It was 1,000 times more powerful than the very significant and profoundly affecting 1995 Kobe earthquake, and it was 600 million times more powerful than the Hiroshima bomb. It resulted in nearly 16,000 deaths, nearly 3,000 people still missing, about 130,000 buildings destroyed, and over 1 million heavily damaged. And the World Bank attributes the direct cost to the earthquake and tsunami at about $235 billion. But perhaps the most significant consequence of this earthquake and tsunami was the damage done to the Fukushima Daiichi nuclear power plant. The Economist reckons that the cost of nuclear decontamination and decommissioning of this plant may be on the order of $600 billion. And even experts at Oak Ridge, Tennessee, who are specialists in nuclear power, fix the cost at somewhere between $250 and $300 billion. So more than the direct costs in this respect to other parts of the infrastructure. Of course, the tsunami was a significant part of this. The tsunami inundated about 561 square kilometers of the TOHOKU coastline. Tsunami heights were anywhere in that area from about 3 to 20 meters. There was about 50 kilometers of run-up on the Kitakami River. If we take a look at the Sendai Plains, which were inundated by the tsunami, where the highest penetration of the land occurred, they looked like what we have on this previous slide. The Fukushima Daiichi power plant was situated on the coast where it was able to exchange heat from the nuclear fuel rod assembly with salt water by virtue of a circulation system. It had a flood and storm protection system, which you see on the lower left-hand side of the picture on the screen. The tsunami came into the protection system. It was about 15 meters high at this location. The actual seawall protection was about 5.7 meter high, and the wave hit the turbine building straight on, creating a splash which was about 46 meter high. Now, the damage that was done by the direct hit from the tsunami actually had a profound effect on the heat exchange system, because there was damage to the condensers which are required for this heat exchange process. And even if the diesel generators, which were located in the bottom floor of the turbine buildings, had been situated at a slightly higher elevation, it's still questionable whether the plant would have been able to function properly. But the diesel generators, which are essential for power when the general electric power is lost, were inundated and unable to function as a consequence of the inundation. The Fukushima Daiichi plant operated with 6 boiling water reactors. At the time of the Tohoku earthquake, there were about 54 nuclear reactors in Japan, 24 of which were boiling water reactors. The other 30 were pressurized water reactors. A boiling water reactor operates by having a nuclear fuel rod assembly. The fuel is uranium dioxide. It's enriched from its normal concentration of U-235 of about 0.7% to about 3%. The fuel rod assemblies were 6 by 6, so these fuel rods are approximately 10 centimeters in diameter, 10 millimeters in diameter, about the size of a pencil, and approximately a couple of meters long. And they, of course, generate a nuclear reaction. Water is circulated at very high pressures, typically at many, many atmospheres, and circulated through turbines where they generate electricity, and then circulated back through a condenser which exchanges heat with the ocean and thereby cools things, and the diesel generators are necessary to keep this circulation going. So without the diesel generators and without the cooling system, there was no cooling for the fuel rod assembly, and they began to overheat. If we take a look at the design of a boiling water reactor, there is a pressure reaction vessel in the center where the fuel rod assembly is located. There is a secondary containment vessel which surrounds the primary reaction vessel, and then there is the actual building which then encapsulates the secondary containment vessel. What happened without the cooling water is that the heat of the fuel rod assemblies began to rise. It got to temperatures of between about 1,000 to 1,200 degrees centigrade. At that point, the zirconium cladding, which encapsulates the uranium dioxide, began to melt. As that melts, it drops the uranium dioxide into the bottom of the primary reactor vessel, and it burned its way through the primary reactor vessels into the secondary containment vessels, which contain quite a bit of water. That water vaporizes, creates an enormous amount of pressure, and in order to prevent the secondary containment vessels from exploding, the gas was released to the building and then to the atmosphere. So that was a nuclear release at that point. As the zirconium decomposes in the presence of water, it actually generates large amounts of hydrogen, and it was that hydrogen that was released into the reactor buildings that caught by a spark on fire and blew up the buildings, which was viewed by many people on the television at the time of the disaster. So if we summarize what happened here, we have units 1, 2, 3, and 4. There were partial meltdowns in units 1 through 3. It started with the loss of electricity because of losses from the earthquake. Without electricity, the plant had to depend upon its secondary electrical system, which were the diesel generators. Those diesel generators were all flooded except one air-cooled diesel generator at a higher elevation, which was servicing units 5 and 6. And probably the reason that 5 and 6, they were down for maintenance at the time, but probably one of the reasons that they also came through fairly unscathed. The seawater cooling system was destroyed. Remember, there was a direct hit on the turbine buildings here, and that's approximately the location for that system. There were partial meltdowns in Units 1, 2, and 3, both in the primary reactor vessel, and then even burned through, at least in Unit 2 and Unit 1 perhaps, in the primary containment vessels. And in addition, Unit 4 was down for maintenance, and the fuel had been recently removed, where it's still quite hot and still can go critical, and was placed in cooling pools. There was a loss of circulation in those cooling pools and quite a bit of fear that you would actually have a nuclear reaction in the spent fuel pools. And fortunately, they were more accessible. They could bring fire trucks in and spray water to cool down those assemblies. Hydrogen gas did leak from Unit 3 into Unit 4, and it was hydrogen explosions that caused the destruction of all 4 of those buildings. There were many independent studies that were done of this disaster after the event, and one of the more famous ones was called the Hatamura panel. This was contracted by the government, the CAN government at the time. And it's chilling to read their report of what actually happened during the disaster. For example, they are required in nuclear situations to have an emergency backup center. And they had an emergency center about 5 kilometers from the plant. When people went to occupy that center and use it as a command control center for actually dealing with this disaster, they found that the telecommunication services were not working. The transportation couldn't get people to and from. They were unable to maintain their fuel supply, and the actual air exchange filtering system was letting nuclear contamination into the air system. So they had to abandon that building. During a nuclear disaster in Japan, the Prime Minister typically took control, and in the Prime Minister's office, there was a 5th floor where the Prime Minister and his cabinet and chief officials from the Tokyo Electric Power Company were making decisions. In the bottom floor, the basement, there were the operational personnel from the Electric Power Company and various ministries, and there was very poor communication between the both groups, and very often some of the messages got mixed up. As you can imagine, without the loss of electricity and some of the batteries going dead over time with respect to the nuclear sensors that they had in the field, they had imperfect information about the nuclear contamination that was surrounding the plant. And in a couple of instances, they evacuated people from areas where there was less contamination to areas where there was more contamination. There's about now a 20-kilometer radius surrounding the plant which has been evacuated. This all had been preceded by some studies academically which were performed in the Sendai Plain and had identified a layer of sand and had dated that layer of sand by radiocarbon in organics both above and below that layer of sand. And what you see in the right-hand side of this slide are some cores that were taken in the Sendai Plain from some trenches that were being dug there. And you can see the layer of sand which is attributed to a deposition of sand from a paleo tsunami, and then you can see the organics both above and below. And because there's such a rich history of information in Japan about the historical past, this particular deposition of sand could be attributed to the 869 Jogan Emperor reign. The date could be fixed to the day, and so they could determine that this sand deposit was placed in 869, and by mapping the extent inland of the sand deposit, they could get an estimate of the size of the earthquake which was required to deposit sand that far inland. And they attributed that earthquake to about an 8.4 magnitude. Now, since the Tohoku earthquake, people have recognized that the inland extent of water does not stop with the deposition of sand. It goes many kilometers further in, just has less energy to be able to carry the sand, therefore you don't find any sand deposition. So in adjusting for what would now be a correction for additional inundation, they are now placing the magnitude of this earthquake at somewhere around 8.7, 8.8, or approximately equivalent to the 9 magnitude earthquake that was experienced in March of 2011. That gives us something like a 1,000-year recurrence interval, and normally with nuclear power plants, you are thinking about dealing with events or at least a 1 in 10,000 year recurrence interval. So quite a bit of recognition of, let's say, the potential for tsunamis, which never quite made it into implementation at the decision-making process. Japan imports about 84% of its energy. Nuclear reactors prior to the Tohoku earthquake supplied about 30% of the electricity in Japan. Japan had planned to increase its electricity from nuclear power to 40% by 2017, and nuclear power was part of its CO2 reduction policy. As of the 5th of May in 2012, all 54 nuclear reactors in Japan were shut down. Of course, 6 of them at the Fukushima power plant were obviously shut down, but all the remainder were shut down. On the 1st of July, one was reopened, and then another one was opened at the end of July. There's currently going to be a vote, a public vote in Japan, in terms of whether they will go forward with nuclear power. The previous government, which just got voted out by the Abe government, which is pro-nuclear, was anti-nuclear. And there's really a lack of a clear direction in terms of what the nuclear power policy will be in Japan, and accordingly, what will generate or supply or replace 30% of the electricity there. This has enormous geopolitical ramifications for all of us. Japan is a major trading partner, a major ally. It's a country that's the 3rd largest economy in the world. And disarray in Japan, insofar as their future energy policy, affects us all. It has, in fact, stolen a bit of our future, because nuclear power, I believe, needs to be part of a plan going forward to have an appropriate mix of energy potentials or alternatives in order to go from an environment where we consume power now that creates pollution for the planet and actually encourages global warming, to a strategy and an implementation of that strategy which is much greener. We need to have that nuclear option, and this event has taken it off the table, and it has affected many of us. If we, in fact, look at the response in Germany, in 2010, Germany supplied 22% and more of its electricity from nuclear power. Germany, of course, has decided to close out its nuclear power in the next 20 years. Switzerland has also, not a location generally recognized for tsunamis, has decided to terminate its nuclear power. It provided in 2008 40% of the electricity for Switzerland. The geopolitical ramifications of this are a work in progress. Japan is also one of the largest exporters in the world, importers of the world of natural gas, and it will have to seek natural gas in order to provide an alternative for the loss of electricity from nuclear power. That, of course, puts it in confrontation with China, which is also seeking natural gas in the area of Indonesia and other locations of that sort. Within Europe itself, where does Germany get 22% of electricity? Well, right now, it's actually burning a lot more coal than it used to burn, and therefore is creating carbon dioxide emissions, which have ramifications elsewise for our future. At the same time we were having the Fukushima disaster and the Tohoku earthquake, there were a series of earthquakes going on in Christchurch area of New Zealand. This is a picture of New Zealand. Christchurch is the 2nd largest city in New Zealand. Population at the time of the first of these earthquakes in the sequence of 4 major ones was about 300,000 people. This is a picture of the Christchurch area. On September 4th, 2010, there was a magnitude 7.1 earthquake. It's called the Darfield earthquake, that occurred about 30 kilometers to the west of the central business district of Christchurch. At the time, New Zealand was able to weather this very significant earthquake next to a very large population center with great aplomb. There wasn't a single life lost. There was about $4 billion of damage, but most of the buildings came through, performed quite well, and New Zealand for a precious 6 months was regarded as the resilient nation. Then, on the 22nd of February 2011, they experienced a 6.2 magnitude earthquake, which completely destroyed the central business district of Christchurch. I lived in Christchurch. It was a place we used to bring our daughter, and it was absolutely shocking to go back and see every major building of significant consequence with serious earthquake damage, and many of the tall buildings at a point where they had to be demolished. That wasn't enough. They had another earthquake on the 13th of June 2011. It was a 6 magnitude, and then another one just before Christmas in 2011, another magnitude 6 located with that epicenter in this picture here. You would not have imagined that 6 magnitude earthquakes would cause so much destruction to a particular location. If the TOHOKU earthquake was a sledgehammer, then the Canterbury earthquake sequence is a hypodermic needle. It shows us that you don't have to be next to a big event to suffer big consequences. You just have to happen to be in the wrong place at the wrong time. There are many scientific reasons for why these earthquakes were so severe, and we'll see some of the repercussions of them, but they generated ground motions that exceeded any expectation of them, at times being greater than the 1 in 5,000 year recurrence interval, and at other times being greater than the 1 in 10,000 year recurrence intervals. They created these strong ground motions because there were forward directivity effects, that is, where the fault ruptures towards the area that's being affected. There was site amplification because the sediments on which Christchurch sits were in harmony with the vibration frequency of the actual earthquake ground motions. And then there were what we call edge basin effects, where there is an amplification of motions. All three of these things occurred at the same time. The consequences were relatively low by virtue of deaths, but profound by virtue of complete alteration of the community. There'll be 1,800 central business district buildings demolished as a consequence of this event. Christchurch has ceased to exist and will never come back as we've known it. 50,000 residences surrounding Christchurch Central Business District have been seriously damaged. We know that the costs now are about $30 billion of direct losses, and that represents well over 20% of the gross domestic product of New Zealand. This is significant because a true measure of an earthquake's significance is its value in terms of losses normalized with respect to people's forward economic productivity. And we've never been in a place like this in the developed world where so much of people's forward direct economic capabilities are being channeled into a natural disaster recovery. And of course, if it wasn't enough for the strong motions, there was massive liquefaction and damage to the underground infrastructure. Let's just look for a minute at some of the strong ground motions. There are 2 ground motion stations, the Christchurch Hospital, the Christchurch College. Those are in the Central Business District, and you see those in the central part of this map. And then there's the Heathcote Valley Strong Motion Data Center, or Strong Motion Recording. And then that big star is where the epicenter of the earthquake was. Now I'm going to look at what we call a response spectra. On the vertical axis, we're plotting the response of a building. It's what we call a single degree of freedom oscillator, but it's representative of a building response, and it's being shown to us in terms of the acceleration experienced by that building. And along the horizontal axis is the natural period of that building, and of course there's a vibrational or period signature to all strong motions, and we put the strong motion into monitoring the response of all of these different buildings with different types of periods. We get what we call response spectra. And the design response spectra shown in this particular projection is the black line. And you can see that the September 4th, 2010 magnitude 7.1 earthquake is the red line, and it just about matched the design earthquake. So things worked very well. And then when we got to the February 22nd earthquake, we have the blue line. And this is a logarithmic scale, so that blue line is sitting above the black line about 50 to 70% higher in terms of the acceleration of those buildings. That's about a 1 in 5,000 year return interval, and the New Zealanders actually designed most of their ordinary buildings for about 1 in 500 years. So totally unanticipated in terms of the magnitude of the earthquake. If we go a little bit closer to the source of the earthquake, close to that star, the Heathcote Valley strong motion is shown over here, both for the Darfield, that is the September 4th, and the Christchurch, the February 22nd, 2011. And you'll notice that blue line is way above, 100% to 120% higher than the black line. These are ground motions that are 1 in 10,000 year recurrence interval from 6 magnitude earthquakes. If we actually look to see what the magnitude of the strong ground shaking at the Heathcote Valley was about 1.2 gravity acceleration, and the vertical accelerations were 2.2 times gravity. That means everything was being thrown up in the air. If that wasn't bad enough, massive parts of Christchurch liquefied. Now, liquefaction is a phenomenon that when the ground shakes, and quite a bit of fundamental research has been done here at Cambridge on liquefaction, the ground pore water pressures are elevated so that the actual stress between the particles of the soil are lost, so that the soil actually, rather than being bound together by contact forces, is literally floating in its own interstitial water. At that point, it turns into a porridge and even a watery-like substance. And if we look at the Darfield, the 4th of September 2004 earthquake, about 52 square kilometers of Christchurch liquefied. That represents about 33% of the built-up area of Christchurch. Can you imagine walking out and finding 33% of your built-up area turned to porridge? The Christchurch earthquake of February 22nd, 2011, almost 100 square kilometers, representing about 67% of the built-up area of Christchurch, and then about 91 square kilometers for the June 13th, about 61% of the built-up area. This, of course, has terrible ramifications on the infrastructure. If we look at the suburb of Bexley on the eastern side of Christchurch, this is an aerial view of Bexley. The road system looks like a canal system. As soil liquefies, water is ejected along with fine-grained materials. In addition, pipelines break, which then supply additional amounts of water under pressure. And you have pictures such as you see on the left-hand side where cars are literally falling into craters where broken pipelines have hollowed out the ground underneath the pavement, and as a car runs over, it's enough pressure to cause the pavement to collapse. So serious damage to the point that the hazard in Bexley has changed from an earthquake hazard to a flooding hazard. There's been so much liquefaction in Bexley that it's settled between 1 and 2 meters. So now you can see the Avon River in front of it. It is now subject to such a severe hazard with respect to flooding that they've completely abandoned Avon. They've completely abandoned Bexley, and also locations like Avonside and so forth along the Avon River, where they've deemed those areas as red zoned. People will never come back to live there. One of the significant stories of the Christchurch earthquake was the effect on the wastewater system. They only have one wastewater treatment plant, the Bromley plant in Christchurch. And there was, of course, during the earthquake, great ground deformation associated with the liquefaction. And pipelines, like you see in the lower left-hand corner, these concrete pipelines at the joints settled and pulled out. And vast amounts of debris came into these pipes and were carried down into the waste treatment plant. The first thing they do is clog up the primary settlement tanks, which have dredging units to them, and they become locked and broken. And then they cause settlement of the clarifiers, damaging the secondary portion of the treatment. And then, of course, all those dikes and embankments that you see in the tertiary treatment lagoons were liquefied and therefore interrupted the flow there also. So they had a very serious problem with their wastewater treatment system. It turns out that this was one of the most significant economic impacts of the earthquake, because replacing a wastewater system requires that you dig a trench on the order of 4 to, let's say, 6 meters, because these are gravity flow systems. They're typically deep to meet the kind of grade lines that are necessary for gravity flow. The water table is about 1 meter below the surface, so you have to put a sheet pile system in so the trench won't collapse. Then you have to put well point systems in to dewater it, and the price per meter is in the order of thousands of dollars to replace this. The replacement of the wastewater treatment system 2 times, because they just replaced it from the September 4th, 2010 earthquake. By the time they had the 22nd February, they had to do it twice, bankrupted their local authority protection plan, which was a security system, an insurance system that had been set up to help municipalities be able to deal with the effects of natural hazards and natural disasters. This is a picture of the water supply system. This is a GIS analysis. You'll see all those green dots on the red areas, which are the liquefied areas, and you'll see most of the damage, of course, is in the liquefied areas. And you'll see that there are about 1,700 ruptures or repairs in the water supply system from just the Christchurch earthquake. And of course, this occurred again and again during the different earthquakes. And this was a segmental pipeline system. It was composed of asbestos cement pipelines, cast iron pipelines, some polyvinyl chloride, which was connected again with the joints. And it was utterly damaged. What you see in contrast with this is the gas distribution system, about 1/10 the size. Rather than being 1,700 kilometers, it was 170. But it was affected by all 4 earthquakes. It was composed of polyethylene, medium and high density polyethylene, same sizes, higher pressures, not one damage, not one repair, only one squeezed off service line from the Christchurch earthquake, thereby demonstrating incontrovertibly that robustness in terms of the product that you put into place has an enormous consequence in terms of its behavior during an extreme event. And it's no surprise that they are going to rebuild the water and the wastewater distribution systems in polyethylene and plasticized polyvinyl chloride. They are going to create thermally welded systems which will be probably among the most resilient in the world as a consequence of this event. And they have the demonstration in the field to prove it. There's a whole bunch of issues associated with insurance in New Zealand. There was a time that New Zealand actually couldn't get reasonable insurance rates because the secondary insurance system just gave up on them. They'd been through 2 major events. Their contracts allowed them not to renegotiate, and it took the Earthquake Commission in New Zealand approximately 12 to 14 months to renegotiate rates. That this is now causing a 4-fold increase in the insurance rates in the country. It's now capped. There's a much more severe cap on things. And as we've seen, there was a profound effect on this local authorities protection program. Let's turn our attention here to hurricanes for a minute. Let's start with New Orleans. It's impossible to talk about New Orleans without talking about the Mississippi Deltaic Plain, because New Orleans is embedded in the Mississippi Deltaic Plain, and the ecology of that plain is the very important primary feature with respect to the survival of New Orleans. If we take a closer look at New Orleans on the Mississippi River, excuse me, I'm going the wrong way. This is a picture down in the bottom part of this slide of New Orleans. The Mississippi runs east-west at New Orleans. And New Orleans is between a rock and a hard place. I'm going to sort of emphasize it here. On the north side is Lake Pontchartrain, which is the ocean, the Gulf. And on the south side is the Mississippi River. And so they're subject to flooding from each one of those. And if we draw a cross-section, which is a little exaggerated through New Orleans, we get this picture. And I call this the Super Bowl of sustainability, because everyone in New Orleans lives at any given time between 2 and 3 meters below the water level of either Lake Pontchartrain or the Mississippi River. And in times of flooding, they're living 5 to 6 meters below those water levels. And New Orleans continues to subside at a rate of about 10 to 25 millimeters a year, depending upon where you're located. And New Orleans is constructed with what we call normally consolidated, or is built on normally consolidated clays. So as you build up a levee, it's a wasting asset. It immediately begins to consolidate the sediment underneath it and sink down and loses its elevation, which is its primary protective feature. If we look at Hurricane Katrina, that occurred on August 29th, 2005, it's the greatest U.S. disaster. 2,000 people dead or missing, over $120 billion of losses. 80% of New Orleans flooded for 53 days to de-water. And enormous impacts on the Gulf of Mexico offshore energy infrastructure and delivery system, which we can't even begin to touch upon in this talk. There was a complete failure of the hurricane protection system, which is well recognized and has been well written up and discussed by a number of people. And so what Hurricane Katrina did is it took what was the governing philosophy for the Department of Homeland Security. Remember, in 2000, the United States went through two major extreme events, one natural and one not so natural. And as a consequence of September 11th, the focus in the United States, and I dare say in the United Kingdom, was on the protection of critical infrastructure. But the conundrum in New Orleans was that it was being protected. It was being protected by the Corps of Engineers, which had responsibility as the Army for building the levee systems and maintaining them through the levee commissions and designing the accoutrements that are necessary to keep them going. And therefore, after Hurricane Katrina, the central philosophy changed and became increasingly more on the resilience of communities, which I think is quite appropriate, and one being more expansive to encompass both man-made disasters or human threats and also natural disasters. Let's put New Orleans in perspective. New Orleans sits next to the Mississippi River approximately just before it drains into the Gulf of Mexico. The Mississippi River drains 41% of the United States. During the great floods of the 20th century, the gauging station just north of New Orleans measured flows at 25 kilotons of water per second in 1927 through 1973. This is 1 billion gallons of water a minute, the entire water supply consumed in New York City per day, flowing by the river at that gauging station. So clearly, the threat from the river is large. The river not only carries water, but it carries sediment, which is essential to regenerate the Mississippi Deltaic Plain. It carries about 200 million metric tons of sediment per year, which, if distributed over 100 square kilometers, depending upon the void ratio of the sediment, would be between 1 and 2 meters deep. What's been happening, as you can see by the bird's foot of the Mississippi Deltaic Plain here, is that sediment and water has been canalized by increasingly larger levee systems to take most of that sediment and dump it into the abysmal plain of the Gulf of Mexico, therefore preventing it from getting into wetlands and restoration of the land, which is required to provide some palliative against the erosional forces of the Gulf. And if it wasn't the river and the sediment, it was the hurricanes. In 2005, we had 28 named storms, 15 hurricanes, as I mentioned before, just in New Orleans, over $120 billion worth of damage. There were so many named storms of that year that we ran out of the English alphabet and had to go to the Greek alphabet. And I kind of call that, for my meteorological friends, sort of the Greek bailout of the American meteorologicals. Some of the major events of that year are shown here. What we have in New Orleans is communities and infrastructure who turn to the government, in this case the Corps of Engineers, which have historically been involved in the protection of New Orleans, to protect them against the immediate source of water, the Mississippi River. Historically building levees and protection structures, cutting off distributaries, canalizing the water flow and the sediment flow. That leads, therefore, to loss of wetlands, which then increase the threat of storm surge, and therefore there's a vicious cycle. And I can tell you that the solution to the storm surge is not the same solution to the river. So both of these do not optimize at the same place. Though this is a work in progress, a work which is going on now to find a balance in terms of how to deal with the ecological issues, the environmental issues, the social and political issues, and of course the technical issues. But the technology is so inextricably intertwined with the environmental and the social issues here that one of the profound lessons we learned about critical infrastructure is that it has a social spine that won't go away and requires serious attention for serious solutions. Hurricane Irene occurred in 2011 on, again, August 29th, the same day that Hurricane Katrina occurred in 2005. It killed 56 people. It caused between $10 and $15 billion of direct losses. It led to the evacuation of portions of Manhattan and the complete shutdown of the New York City transportation network, the first time ever. It was record flooding, and it was a near miss. When I started to give this talk, I talked about Hurricane Irene. Now, and when I started to give this talk, the possibility of flooding in New York City, or the flooding of New York City by virtue of a hurricane, was a possibility. Now I'm giving the talk, and flooding of New York City by a hurricane is a boundary condition. If we now look at Hurricane Sandy, over 120 killed, $60 billion of property and business losses. Again, the evacuation and shutdown of the public transportation system. Wall Street shut down for 2 days. That hadn't occurred since, I think, 1886 when there was a blizzard. And record flooding again, surge in this case, and this time a direct hit. And if we look to see what happens with hurricanes, in the northern hemisphere, they spin counterclockwise. So they tend to parallel the coast. This hurricane occurred in October, and we get sort of late hurricanes that get to the northern part of the United States. And as they parallel the coast, this counterclockwise spin creates a velocity, a tangential velocity that comes off this rotation here. Let's see if I can get this thing to go. It doesn't seem to be going. Anyway, if you look at where it's rotating, you'll see a velocity that as this hurricane is coming up the coast, paralleling it, is sending wind into the coastal waters and piling up the water to create surge. What happened during Hurricane Sandy, because of a low that was moving across the United States, this hurricane got sucked in at the same time. So now both the center of the hurricane and the spin are amplifying the velocity of the wind, which is coming on shore, and piling up the surge, which then made a direct hit in the harbor of New York City. And if we look at the evacuation zones for New York, they called for, if you look at these maps, both the dark orange and the sort of light orange area, Zone B, that somewhere in between was exactly what was flooded. Cornell University is now in partnership with the Technion building a New York City tech campus on Roosevelt Island, which I've shown on this picture, and that was underwater, so we have some thinking to do about natural hazards also. And this is a picture, if I go back, you see the Battery, which is the lower part of Manhattan there. This is a picture of the hydrograph at the night of the hurricane. And you'll see that the peak flow is about 4.23 meters, and it's occurring on a tide. As the tide peaked, the hurricane surge came on. So if we subtract the 6.1 oscillation about the neutral point from that 4.23 meters, we get about a 3.6 meter surge, and then we have the additional water that's piling up because of the oscillations from the tide. Now, if I take that 4.23 meters and I do a simple GIS analysis and I place that on top of sea level in this Landsat image of the New York City area, this is the amount of land that was underwater in a first order analysis. About 35% of the land, highly developed, highly critical areas with critical infrastructure, completely inundated. Here's LaGuardia Airport. I fly there a lot from Ithaca, and was interested to know that I would need a kind of a ski plane to land. And then if we come closer, we'll see that this was the inundation around the lower portion of Manhattan. There's the Battery, there's the World Trade Center. The World Trade Center was inundated. This location, this white dot that you see just south of the New York Stock Exchange, so the New York Stock Exchange was above water, but the telecommunications going into the New York Stock Exchange were underwater. Verizon, the same building that was damaged and couldn't supply telecommunications in 9/11, was flooded in its first floor and 5 basement levels by Hurricane Sandy. Now, they had moved the diesel generators. They had learned from Fukushima and from Hurricane Irene the year before, and had moved the diesel generators, which had been required by building code, or at least the interpretation at that time, to the 10th floor of the building. They however, at the 5th floor had left the fuel, which they're required at the bottom floor of whatever it is, they're required to put their fuel. And then the pumps were in the 2nd basement level, so they're 4 stories and 5 stories down. And of course, the water got into the basement. The fuel is lighter than water. The tanks are not full either. They floated up, they disengaged from the fuel lines, and then the pumps got inundated, and they couldn't work properly. So although the diesel generators were functioning just fine, there was no fuel to make them operate. And so you lost the major central office for Verizon at the World Trade Center, and you lost the one at Broad Street, which is that white dot that you see, and that was the entire Securities and Exchange Commission data source going into the New York Stock Exchange. What Verizon did is they have their own fuel trucks. They dispatched them to the site. They got a pump and they got the fuel. They put it out on the street and they pumped it up to the 10th floor, and they got their diesel generator going about 36 hours after Hurricane Sandy, and were able to send information into New York Stock Exchange by the time it opened 24 hours later. If we look at the effects of the inundation on the underground system in New York, the New York City subway system, if I take this inundation map on the left and I transpose it over to the right and then I make it go transparent, you can see the portions and the tube stations that were underwater as a consequence of this event. And I'm going to bring them up again. The major source of damage was that little red South Ferry at the lower portion of Manhattan and the Whitehall stations. Water poured into those stations, salt water, which had dramatic impacts not only in flooding the stations, but having serious corrosive effects on the switching gear, the lighting, ventilation, anything electronic, signaling and so forth. And the R line, that yellow line, took about 2.5 months to restore. It was completely inundated. In fact, that wasn't the only tunnel that was flooded. 7 subway tunnels, the Brooklyn Battery Tunnel, the Midtown Tunnel, the Port Authority and Trans-Hudson tunnels, and the Holland tunnels. And those are just the passenger and vehicular tunnels. There were many train tunnels, Amtrak and so forth, that I don't even have data on. And you can see that the interruption of the mass transit system here, by leaving a gap with these lines, which are out, that you see in this picture, and I'll now emphasize them, created a barrier and an inability for people to move from Brooklyn into Manhattan and vice versa in portions of Queens. New York City was literally paralyzed for a week to 2 weeks with people unable to move from one part of the city to the next. In addition, we remember that there was a surge of about 3.6 meters, and the Consolidated Edison Company, which supplies electricity for Lower Manhattan, had positioned their substations at elevations that were at minimum about 3.6 meters. And unfortunately, Hurricane Sandy came in at about 3.6 meters, but with the tidal effect, got up to 4.23. That inundated one of the 138 kV transformers at their 14th Street substation, causing a major explosion. And then they just shut the system down south of 36th Street and 42nd Street, so the entire southern part of Manhattan was without electricity. The reason, for example, that nobody's pump worked in any of the basements, unless they had backup diesel, and many of them had the pumps and the fuel canisters float and be destroyed, so that the diesels were functional and they're not getting fuel. The steam distribution system in New York, which is a wonderful system for cogeneration. It allows you to capture secondary heat and generate additional energy sources in New York City. It became a bit of a Frankenstein because it carries steam at about 200 degrees centigrade. The steam has pressures anywhere from 1 to 2 megapascals. And if it comes in contact with cold water, it condenses. And you therefore get water bubbles in this thing, which then will increase the internal pressure, and you can have underground exploding steam lines from this. So they had to shut down large portions of their steam system to make sure that they didn't become problematic with respect to damage and destruction. And then finally, we have some hurricane simulations. This was done by a professor at Princeton University, Ning Lin. What I want to show here is the folks at Princeton simulated by virtue, and also at MIT, Kerry Emanuel was part of this team, simulated storm tracks with an environmental wind model that was tied to atmospheric hurricane deterministic model, and then tied to hydrodynamic models to be able to determine surge levels. And they ran about 7,500 simulations. This is the way we do things these days, to create as best we can in physics-based models the actual occurrences as best as we know them, to kind of get a statistical sampling of what might happen. And this is the distribution curve that you see, and you can see Sandy sitting way out there, and if you even look further to the right, you'll see these rare events that are on this distribution curve. And you'll see that it's 3.6 meter surge. This is about a 4,500 year return interval according to the Lin et al. Analyses. But what I really want to draw your attention to is the characteristic of that distribution curve, because that's capturing all of these events. And we tend to think that we understand the distribution of extreme events for purposes of design, and one of the great contributions of the last 25 years has been risk-based analysis and probabilistic assessment. But we really don't understand the tails. Those distributions in the tails are almost point sources, and we draw a continuous line from them, and we borrow area from the center of the curve, and we plaster it out on the ends of the curve, and we come up with a one-sum game and say that we understand the probability. Well, it may be that mathematically we do, but I think we don't quite get it in terms of the implementation of that probability, and we don't quite get it at times by having a false sense of confidence from the center part of the distribution curve, where we've done some great things. And one of the messages of this lecture is to be very careful about tails. So let's then go to the new normal. The new normal is that it's anything but normal. We're certainly not dealing with normal distributions, and we're certainly not dealing with normal occurrences. Generally, nuclear power plants are targeted to have a failure probability of about 1 in a million per year, at least. If we take the 5 major nuclear releases in the last 14,000 nuclear reactor years, that is the 3 at Fukushima, the 3 Mile Island, and the Chernobyl, that's 5 divided by 14,000, giving us about 10 to the minus 4 per year. So we're about 2 orders of magnitude off in terms of what we think is the security level that we're designing for, and what reality has in turn demonstrated to us. There's a person at Duke University, Henry Petrosky. You may have read some of his books. He just wrote a book called To Forgive Design, and he has a wonderful example in there about the space shuttle program. When asked at the beginning of the space shuttle program what was the probability of failure, NASA said about 1 in 100,000. 25 missions out, they had Columbia. So it was really 1 in 25. Another 113 missions out, they had Challenger, and then they had Columbia. So they had another major failure in the system. And when they closed out at 134 missions, there were 2 failures, or 2 divided by 134, or about 1 over 67. A far cry from 1 in 100,000. So in addition to the misperception, and maybe the misapplication, and maybe the misunderstanding of tails, we have problems that are compounded by institutional constraints, by politics, by lack of perspective, and as we see in Hurricane Katrina, and as we see in the Fukushima Daiichi disaster, sometimes just plain dysfunction. So the new normal, from my perspective, is that there is infrastructure which is just too big to fail. If we could go back and redo New Orleans, if in Japan we could go back and redo Fukushima, surely we would do it differently, because the consequences of those failures have been really unsustainable. And so what I think we need to do is we need to seriously reassess the risk related to critical infrastructure with some humility about what we know and what we don't know. And we also should examine not only the consequences of probability, which are based on events, and the cumulative frequencies of whether an event will occur or not, and also do a consequence design. So the probabilistic might be we have a 1 in 100,000 chance that the tsunami will get over the storm protection barriers. What if it does? Then how do you protect yourself from that stage? And that's what I would call a contingency type design. We also need to reassess and identify critical infrastructure. Now, as an academic, I spend a lot of my time trying to define what critical infrastructure is, and I can assure you that every time we write a proposal, it's all critical. The point is, some of it's more critical than others. And so it's everyone's created equal, except some of us are more equal. And so therefore some infrastructure is more critical than the other infrastructures. And we need to identify that. And the way to identify that is at the local level. It's not at some governmental or some sort of oversight committee definition of it. One of the things I've learned about infrastructure in my career is that infrastructure has universal precepts and characteristics, but its character and its personality is local. I'll give you an example. The water supply of New York City, which is operated by the New York City Department of Environmental Protection, operates on the same principles of the water supply in Los Angeles that's operated by the Los Angeles Department of Water and Power. They're both gravity feed systems with occasional topographical highs at which pumping has to occur. They both have the same types of pipe. They both have 70% of their pipe in cast iron. They both have the same valves. They both have the same reservoir issues. Yet nobody for 1 minute from Los Angeles would ever dream of telling somebody in New York City how to operate their water supply. I guarantee that. And nobody from New York would do the same. Our infrastructure is suffused with personality and institutional cultures. And therefore, we need locals to understand them and to advocate for them. There's a great example of this with the bond issues in California, where local communities in the Bay Area advocate for more resilient infrastructure and have been successful in upgrading their water supply, their transportation networks. And I look to San Francisco and the models in California as one of the great in the world, where the people and local advocates make decisions, raise their sales tax for a few years, and put critical infrastructure into place. So the definition of critical is this. You have so many infrastructures. Which one is the most critical? And you only get one choice. That's what every community does. That's the hardest means test in the world. And if we don't do that, we run the risk of saying they're all critical and dispensing or dispersing with our economic largesse. Look, we can't afford to fix all infrastructure, but we can't afford not to fix some of it. So I think everyone, every community, should ask themselves the hard question of what's really important here and take some steps, both with probabilistic and contingency design, to make sure that they're not going to be impacted and lost in a critical situation. And that's what I call punctuated resilience. Now, America's next Fukushima is the Southern California water supply. The southern part of California has 22 million people. It's the 11th or the 12th, depending upon what economist you talk to, largest economy in the world. And it receives 70% of its water from outside the area. It receives water from the California Aqueduct, where in California we take water from the Sacramento River Delta, the San Joaquin and Sacramento River Delta, in the northern part of California, and we take it 750 miles south to supply Southern California, and that is subject to risk, just that route itself, and also the damage and the dangers that exist in the Delta. Los Angeles aqueducts supply water, and the Colorado River Aqueduct. There's about a potential of 30% groundwater that can be tapped in the Los Angeles and Southern California area, but a lot of that is actually contaminated. There are contamination plumes, and people won't necessarily take that out of the ground because it's there volumetrically, but it's not necessarily there in effect. So if we were to have an earthquake on the San Andreas Fault, now in 2008 there was an earthquake emergency exercise, the largest that ever occurred in the United States, and involved 5.4 million people. That's called the Great Southern California Shakeout, and the U.S. Geological Survey created this simulation of a fault rupture starting at the Salton Sea. You'll notice we're about 1 minute into the propagation along the San Andreas Fault of a 7.8 magnitude earthquake with forward directivity towards Los Angeles, to Lake Hughes at the northern extent of this. And you can see the strong ground motion and the waves being trapped in the Los Angeles basin, where they do quite a bit of damage. That type of earthquake would literally sever every external supply to Southern California. The California Aqueduct carries 49 billion cubic meters per year. The Los Angeles aqueducts carry 390 million cubic meters, and the Colorado aqueduct carries 900 million, and they would be severed, and it would take more than 6 months to return that water supply. So we would clearly have a problem here. Yet this problem, I reckon, could be fixed with about $2 billion. Well worth the price for the insurance and the protection that it would supply. And we're currently working very hard and making good progress in getting these three entities to talk to each other, because the problem is not so much how to fix it technically, it's how to get agreement interinstitutionally as to who's responsible and who should take the first lead and how to coordinate their energies and activities. This is the Los Angeles aqueducts crossing the San Andreas Fault at the Lake Elizabeth Tunnel. The Lake Elizabeth Tunnel is about 3 meters wide at this location. The simulation of that fault rupture that I just showed you created a fault rupture at about 3.3 meters at the Lake Elizabeth Tunnel, so you can see clearly that both 1 and 2 aqueducts, which flow by gravity in this particular location, would be lost. We are doing something as a lesson from New Zealand. We don't know how much a fault's going to rupture, so there is a probability distribution associated with that fault rupture. It may rupture at 3.3 meters, but it may rupture at 2. It may rupture at 1. So what we are doing right now in LADWP, through the efforts of Craig Davis, who's one of their chief managers and geotechnical leader, their leader of their geotechnical engineering, we're actually taking high-density polyethylene pipelines, about 600 millimeters in diameter, 2 of them, stacking them side by side on the side of the Lake Elizabeth Tunnel. And if that tunnel were to close, it could close by 2.5 to 2.6 or 7 meters, squeeze these polyethylene pipelines into ovals, and you would still be able to put water through there, plus you could pump it, and therefore you could send a lot more water with respect to pressure. So I like to call this as the sort of the poor person's solution to shaving some of the risk associated with the loss of water supply in Los Angeles and exporting some of the lessons from New Zealand. If we were to go back and look at New Zealand needs to export the lessons from Christchurch to Wellington, because the Wellington Fault runs through Wellington, and virtually every infrastructure in the nation's capital would be seriously impacted. They have a similar liquefaction hazard, and they have all the same pipelines in their water supply and their wastewater system that we saw so heavily damaged in Christchurch. Furthermore, the electricity in New Zealand is produced by hydroelectric power primarily in the South Island, and is then transmitted under the Cook Straits to the North Island, and the major user is Auckland, many, many hundreds of kilometers away. And an earthquake, either on the Wellington Fault or the Wairarapa Fault, would trigger submarine landslides that would take out all of those power cables. So you would actually sever that electricity connection. And of course, an earthquake in Wellington would decapitate the government. There are a number of critical infrastructure projects which I've identified and talked about and we're working on in the United States. I think this is very important to establish a hierarchical idea of what's critical and what needs to be fixed. Now, in finishing this, there's a few other things on a more general basis that we need. We need a multidisciplinary dialogue and a plan to solve this problem. Not just engineers can solve the problem, but we need planners and social planners and economists and so forth. And I've noticed that there have been a number of conventions that have been held in the recent past to look at areas of great importance to critical infrastructure, such as the Future of Cities 2011 at Chatham House, an intelligent infrastructure held by The Economist in New York City in February of 2011, and the Rockefeller Center symposia on the future of the city, or the century of the city, at the Bellagio Conference Center, and putting out this book. If you haven't read this book, The Century of the City, it's a brilliant read, very, very worthwhile reading. But let's just see how many engineers they invited to these particular conferences to decide the future of cities and critical infrastructure. No engineers of the 28 speakers at Chatham House, less than 10% of the participants at Intelligent Infrastructure. I think the Intelligent Infrastructure Center has some work to do here in terms of PR, because after all, The Economist is a British, what they call newspaper. And then 3 out of 300 participants, so we got 1% in for the Bellagio Centers for the century of the city. So clearly we need to broaden the dialogue here, and we need to start to engage and get planning and decision makers to start to consider engineering in at least a more programmatic way. Financing. Look, we simply can't afford to fix the broken infrastructure that we have. It's just beyond our ability to catch up. And so the standard models and the conventional models of bond issues and so forth are fine, and we can do some creative things with them like they do in California, like bypass their state legislature and get some money apportioned to things that they're concerned about, but it's just inadequate. We have insufficient liquidity unless we can entice the private markets. We really have to tap the investor community with creative ways to be able to finance infrastructure. Infrastructure bank has been floated as a great idea, where you combine both private equity and public equity. And what I like about this concept is that the private side, which is a more discerning side, the less pork-oriented side, will be able to decide on what are the critical infrastructure projects that they're going to invest in. So we'll have a little more objectivity in the selection process. And of course, public-private partnerships are something which is touted and talked about, and a lot of creative things are being done to have firms design, build, and construct, and finance, and own, and operate for a number of years, and then turn things back over. I'm not sure we've thought out the consequences 20 or 30 years down the road when they're turned back to the municipal authorities, but still, it's a good thing to do by tapping some private equity in the near time. And then we need to reach out to leadership and public. It's our responsibility to tell the story of critical infrastructure and the importance of critical infrastructure for the public and the leadership in general. This is a picture of Ray Nagin, the person at the center of this screen, and then Mitch Landrieu. Both of these people ran for mayor 6 months after Hurricane Katrina in April of 2006. And Ray Nagin won. And Ray Nagin took off the table, and he had good political and personal reasons for doing that you would ever have any land in New Orleans be given back to the sea. All was going to be reoccupied. Now, I sat on an oversight committee of the National Academies for 4 years, and it was a multidisciplinary group. We had climate modelers and social scientists and economists and geotechnical engineers and structural engineers and hydraulic engineers and so forth. And of 16 people were unanimous that New Orleans occupies a footprint that is unsustainable. In fact, after spending $15 billion to redo the hurricane protection system, which is vastly improved, it still won't protect against another Hurricane Katrina. It's still not high enough to be able to deal with that surge. So unless we make some hard decisions about what is natural and what is communal, we are not going to quite get there, and I call this, again, a work in progress. We have lots to do to reach out and communicate. And so let me end this talk by saying that we need to rethink critical infrastructure, we need to subject it to some means tests, and we need to stop thinking within the zone of comfort at the central part of the probability distribution curve. I believe that we need to look at things probabilistically because it's a great way of doing it, but we need to have humility about the tail of the distribution and also look at critical infrastructure in terms of contingency and in terms of consequence. So a combined probability consequence analysis, I think, is at least on the order, and we need to identify that part of infrastructure which is most critical for us and find ways to finance its reconstitution. And so I'm going to end this talk with the concept of punctuated resilience, which is to protect what is possible beyond what is probable. Thank you very much.